we have equation here for the Poisson distribution. How can we find the sufficient statistics for the parameter lambda? So the parameter here is lambda. So for we to find the sufficient statistics, this is what we do. We have to factor this out. That means by taking the product. So this is what we do. You see the function x1, x2 to xn, the parameter is lambda, will be equal to lambda x1 exponential lambda 1 all over x multiplied by lambda x2 exponential minus lambda all over x multiplied by, that's how it continues to give us lambda xi exponential lambda all over x. So since we have this, we can combine this to get x1, x2, xn, and the parameter lambda to give us, if we sum the whole of this, we get summation xi's, I ranging from 1 to n, exponential. If we sum this, you get n lambda all over. You bring this together to give you x dot xi, so these two dot xi, which is the formula for this. So what we have to do is just to factor this out. How do we factor this out? You come here, you first write out our function f of x1, x2 to xn, and writing out the parameter. You see that this function here, if we are putting it out into two components, like the definition for sufficient statistics, we can write it as this: lambda summation xi, that means I ranging from 1 to n, exponential negative n lambda multiplied by 1 all over x1, x2, and x3 multiplication. So this automatically becomes our new x1, x2 to xn, which can also be written as this, because it's that function that depends on the parameter lambda. So we can write this as this lambda. Why this function is the h that does not depend this function does not depend on the parameter lambda. Hence, we can write this as mu summation xi lambda and this can be written as this x2 xn. So it means that the summation of xi is a sufficient statistics for lambda. So this is how we can get the factorization theorem for the Poisson distribution. It's quite simple.